Ladies and gentlemen, we are back. Now we start with the really fun, mind-blowing stuff. Hydrocarbons and haloalkanes. And by now, you're probably going to start crying. No, we'll start crying together, I promise. This freaked me out in mortuary school, too. So organic compounds are divided into different classes of compounds based on the elements that are present and the functional groups that may be present. The next slide is a chart I found at Biology Corner. Check that place out to give you an idea of the number of compounds that are out there. And epic fail. Okay. Later on, this section will be fairly useful when we study organic compounds like carbohydrates, lipids, and proteins. So know this is here. Cool. Hydrocarbons. The simplest of the organic compounds. They're a large group of compounds called the hydrocarbon. I'll learn to speak again here in a second. A hydrocarbon is an organic compound containing only the elements carbon and hydrogen. Gee, hydrocarbon, carbon, and hydrogen. That's pretty easy. There are further subdivisions according to how the carbons and hydrogens combined. I promise you I've not hit the flask before I started lecturing. Compounds characterized by open chains of carbon-to-carbon bonds are considered to be acyclic or aliphatic. Those compounds whose chains of carbons form a ring are considered to be cyclic or aromatic. Hard one. If it's a line, it's acyclic, does not form a circle, or aliphatic. If it does form a ring, it's circular, cyclic, or aromatic. Note card it. The aliphatic, non-circle forming hydrocarbons are further subdivided, oh my head, into classes based on the type of bonding that is present between the carbons. Here's a nice little chart. These are the type of things you should be doing. Or you should be looking on the internet to find, because that's how I found these things. And if you have the slide, if you have the PowerPoint, you can just put your mouse over the picture. It tells you the owner of the picture and where you can find it and read the website it was from. Some of these will blow your mind, but they're still cool. First up, alkanes. The alkanes are acyclic hydrocarbons. They are aliphatic hydrocarbons in which all of the carbon-to-carbon bonds are single covalent bonds, single bonds. The alkanes are considered to be saturated hydrocarbons because they will hold no more hydrogens. The word alkane comes from a prefix and a suffix. The prefix alk refers to the aliphatic hydrocarbon, and the suffix ane refers to the presence of all single bonds. The characteristic type of reaction for the alkanes is substitution or replacement, since it's going to be necessary to replace a hydrogen to combine the molecule with something else. You got to get rid of an H to add anything else. Alkanes have two AKAs, the paraffin series or the methane series, and that gets its name because of the first member of the class, methane. All of the members of the alkanes have a molecular formula that may be determined by the general molecular formula of the class, CnH2n plus 2. And the integer n is the number of carbons. So if I add 1, I get CH, 2 times 1 plus 2. Well, 2 plus 2, wait for it, 4. Okay, so methane, 1C, check, 4 H's, 1, 2, 3, 4. Bam, that's how that works. And if I add 2, I get C2, H2 plus 2. Multiply first, so I get 4 plus 2, right? And then it becomes C2, H6. So figuring it out an alkane, memorize that general formula, because you probably know that since that's easy stuff, I should probably be asking questions about it. You should be able to compute what a formula would look like. In determining the general molecular formula, you simply substitute number of carbons, which I already did for you, so I'm not going to do it again. Yeah. When naming the alkanes, we use the same rules for nomenclature, that's such a cool word, established by the International Union of Pure and Applied Chemists, also known as IUPAC. Chemists just do not come up with cool acronyms. Here are the rules. First, name the longest chain of carbons. So find the longest chain, the most C's in a row, start there. Then, if there's a carbon side chain, name it, smallest to largest, and give addresses for all side chains using small numbers. Oh my God. The name is always written from right to left, but it is read from left to right. The carbon chains are always identified by the appropriate prefix for the number of carbons in the chain. The longest chain has the suffix ane because we're dealing with the alkanes. And carbon side chains are also called radicals. Oh, that's what a radical is. Would have been helpful to explain that back before they started using the term in the book, but BAMO, radicals. And they are identified by the appropriate prefix followed by the suffix YL, which identifies a radical carbon side chain. Okay? A carbon radical side chain. So it gives you the prefixes. Professor Finn, do I have to memorize? Yes. Yes, you do. Ha, ha, ha. Memorize it. Suffixes. Not nearly as hard. 2. Ane, ill. Okay? If it's all got single lines, it's an ane, because you're going to see the enes, the ines, and the rest later. And then side chains, ills. But the alkies, meths, eths, props, butes, pents, hex, heps, ox, nons, dex. Yes. Many of these should not be hard. You can probably fake it because many of these have, regular numeric Latin names. So name the alkane of 1 carbon. 1 carbon is meth. You can tell this book was written before Breaking Bad, huh? So, it's going to look like that. 1 carbon. So it's a 1 carbon chain, meth. Saturated are all single bonds. That's what we're dealing with. Ane. So meth, ane. Cool. Got it. 2 carbons. C-C. Well, connected by a single 2 carbon chain, ethane. See how this is working? Not as hard. Stop crying. It's all good. I stopped crying when I started making the lecture, which will tell you something. So name the following alkane. All right, deep end of the pool. Appreciate that, Finn. Yeah, see you at your car outside tonight. Ba-da-da. Not hard. Step 1. What was it? Remember what step 1 was? Determine the longest chain. Shouldn't be hard. Look for the large number of C's. Okay? There they are. So if we do this, we have 1, 2, 3, 4, 5, 6 C's. 6 C's. Hex. Okay, so we start with hex. All single bonds, because that's all we're dealing with right now. All single bonds. See that? So we're dealing with hexane. Hexane. Cool. Crap. Side chain. Son of a... Well, what do we have? 1 carbon. 1 carbon. What's 1 carbon? Meth. Person really likes meth. But it's a side chain, so we know it's methyl. Okay? Methyl. So we're dealing with some sort of methyl hexane, but position matters. So what happens next? We have to indicate where the side chain actually appears. Well, this is where that smallest number silliness comes in. Because if we start from the left and go right, we get 1, 2. Okay, cool deal, pickle. We start over here, 1, 2, 3, 4, 5. Well, crap. Smallest number applies. So in this case, we have to use 2. So we are dealing with 2-methyl hexane. Okay? So remember, we go back to the rules. It is always written from right to left, but it's read left to right. Well, if we read it right to left, we get hexane 2-methyl. Doesn't make any sense. But if we do it left to right, 2-methyl hexane. Much better. The alkenes, Kenes, are aliphatic, okay, acyclic hydrocarbons, straight line, in which one of the carbon-to-carbon bonds is a double bond, double covalent bond. The alkenes are considered to be unsaturated, because at any time we could bust that up and add a hydrogen. Okay, we could add hydrogens to it. The prefix alk, once again, refers to the aliphatic hydrocarbon, but the suffix ene refers to the presence of at least one double bond. The instant you get more than one double bond, triple bond, whatever it is, it changes the end, changes the suffix every single time. The characteristic type of reaction is addition, since it would be possible to add across the double bond when combining with another substance, adding in a plural. There are several other names for the series, olefin or ethene series, and we're going to see that a lot of these series get the name from the first one there. General molecular formula of this class is CN2N. With the alkanes, you simply insert the number of carbons for the N to produce the molecular formula. I think that might be a typo. Should have said alkenes, so don't go crazy. Okay? Just like, or as with the alkanes, I'm not losing my mind, I'm just losing my sanity. You simply insert the number of carbons. Boom. If I have, grab my handy dandy little expensive digital pen here. C3, 2, 3. All right, so it's going to be C3H6. Boom. That's how I determine stuff like this. Not hard. So there are rules, okay? There are rules. These should look familiar. These should look familiar. You give the address of, so again, first find the longest chain. Give the address of the double bond using smallest numbers. And if it can't be confused, don't worry about it. We'll see what it means. Number the carbons in the longest chain so that the carbons on either side have the smallest addresses. You'll see what it means. It's not hard. The address of the carbon next to the bond, which has the smallest numbered address, is the address of the double bond. So if you read it left to right, right to left, you go with the smallest number. Same exact sort of thing. I'm going to work you through it. With the double bonds between carbons 3 and 4, address is going to be 3. Name the carbon side chain, and this is where things get a little hairy. We worry about that smallest number when it comes to the double bond. Once we determine where the double bond is from that point forward, any side chains have to be named by counting in that same direction. You're going to see it. So give addresses for all side chains using the addresses for the carbons as determined by the address of the double bond. Names are always written from right to left, but is read left to right. Carbon chains are always identified by the appropriate prefix for the number of carbons in the chain. Longest chain will have the number preceding the prefix, blah, blah, blah. Carbon side chains get the YL. And remember, since we're dealing with at least one double bond, it has to have ENE. And I'm not going to go over the 2 or 3 carbon alkanes because it just is what it is. If it's got 3 carbons, one with the double bond, knock yourself out. I mean, that's not hard. Oh, my buddy Steve Hardray. I love meme generators. I love meme generators. When the 4 carbon alkene, we finally see a potential that there is confusion because the double bond could be between 1 and 2 or could be between 2 and 3. Well, we just said it. Don't overthink it. Between 1, 2, 3, 4, 5. So in this case, it's going to be between 4 and 5, or it's going to be between, let's get rid of all this, 1, 2, 3. We're going to go 1, 2, 3. Okay? 1, 2, 3. And we go with the smallest number of that. So it's going to be a 2. Okay? We know it's a 2. 1, 2, 3, 4, 5, 6. 6 carbons. So we jump all the way back, blah, blah, blah. 6. Okay? See how this is working yet? Let's get rid of all the dots. So let's go crazy. Let's go crazy. We just started with this. So 1, 2, 3. 1, 2, 3, 4, 5, 4, and 5. So we know it's going to be 2. 1, 2, 3, 4, 5, 6. We go back. I think that's hex. Let's look at it. This is what happens when you get old. You forget crap. So 6, hex. Okay. 2, hexane. That's great. Spelling it the German way. Hexane. Almost did it again. Oh my God, my writing is even worse than my spelling. So then what do we have? We got this guy. Damn you, side chain. Well, if we count normally, we have 1, 2, 3, 4, 5, 6. Between 1 and 2. Professor Finn, we go by the smallest numbers. No, this is where this gets miserable. Okay, this is where it gets miserable. Because since we determined the double bond from this direction, we must count from this direction. 1, 2, 3, 4, 5. 5 methyl. Okay, 2 hexane, 5 methyl. Well, we're going to have 5 methyl, 2 hexane at the end, more than likely. Now, I don't remember. I made this slide, about a week ago. We'll find out by the end. Find out by the end. So hexene, because your professor's an idiot and forgot we're dealing with double bonds, right? Hexene. I walk you through, you see? We have to count the 1, 2, 3. We see the methyl because we've seen the methyl before, so who cares? And always start from wherever you started numbering. Okay? So wherever you determine this double bond, that's where you are obligated. You are obligated to then determine it. Because if we were to rewrite this, okay? If we were to rewrite this, and I do this up here, we're going to have whoops, double bond right there. And then we have to put the side chain where the side chain goes. So in this case, on 5. So it is extremely important that now that we are dealing with any of these double, triple bond bad boys, that we always start from where we started counting. So the name we have here is 5-methyl 2-hexene. 5-methyl 2-hexene. Alkynes. Alkynes are aliphatic, acyclic hydrocarbons in which one of the carbon-to-carbon bonds is a triple bond. The alkynes are considered to be unsaturated because, just like the alkenes, you could break that triple bond and add more. So now you should know what an alky stands for, and YNE refers to triple bond. Several alternate names, the acetylene series, the ethyne series, and it gives you the general molecular formula, which again, you substitute a number for N and you get a formula. Well, there is nothing different about what we are doing, okay? With the alkenes and the alkynes, you follow the same number of rules. You follow the same exact things, determine where that triple bond is, and away you go, okay? That's the big thing, is you determine where the triple bond is, you start counting from that direction, and then you list your side chains, et cetera, et cetera. So you should be able to handle just about anything I throw at you. Aromatic hydrocarbons are those organic compounds which are comprised of only the elements carbon and hydrogen arranged so that we have a ring. Sometimes they're called cyclic or closed chain. We also know that they're also called aromatics. It's in the title. And the carbocyclic hydrocarbons are those with only carbon in their rings. The cycloalkanes. The only thing that changed is we add CYCl. So we have cycloalkanes or cyclanes, carbocyclic hydrocarbons, similar to the alkanes, except instead of a line, they form rings. Okay? And you can see the line drawings. So if I'm forming a quote-unquote ring with 3 carbons, C, 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 all single bonds, it makes it an alkane, it forms a triangle. They start adding things, it becomes more and more circular. All members of the cyclanes have a molecular formula. The smallest of these is cyclopropane. It's a 3-carbon ring, 2 hydrogens attached at each carbon, and single bonds between all other carbons. Obviously, cyclo refers to the ring structure, prop refers to 3 carbons, and suffix ane refers to the single bonds joining them. Cyclobutane is its next member, ring of 4 carbons, 2 hydrogens, etc. The cycloalkenes are carbocyclic hydrocarbons similar to the alkenes because double bond, but they form a ring rather than a line. The most prominent member is benzene. Benzene is a ring of 6 carbons with what appears to be alternating double bonds between the carbons and a single hydrogen attached to each carbon. So it shows you where the single and double bonds are. Fairly recognizable molecule. A benzene ring is probably one of those givens. You should just look at it and go, oh yeah, I know what this is. Boom. Benzene is C6H6. And hey man, you know, it tells you that, oh, the problem is in reality, the double bond, single bond thing doesn't really happen that way. What's actually happening is that the alternating double bonds are resonating between all of the carbon. So think of it like at any one given time, it's bouncing back and forth between double and single. This is called resonance. Okay, this is called resonance. Due to the resonance that occurs in benzene and its family of compounds, the type of reactions they undergo is not what one expects from an unsaturated compound. Benzene and the majority of the aromatic compounds react not by addition, okay, but instead by replacement of the hydrogen. Something swaps out. So the first ones, the alkyl halides. The alkyl halides are haloalkanes. You might remember that from the title of this chapter. Appear as an alkane that has one or more of its hydrogens replaced by a member of the halogen, whatever family, found in group 7 of the periodic table. So if I take any of the halogens and substitute them for a hydrogen, I bump into the haloalkanes. A group of this class of organic compounds has the general formula R-X. The term R refers to the alkyl group, and the X stands for the halogen. So whatever I am doing, if I go back and look at all of these, you can see that I still have alkanes. I have single carbon chains. I'm going to do everything that I would normally do. Count the number of carbons, and I got 4, so I have no side chain. Who cares? So this right here, all of this is my R. This is my X. Okay? No different. R, X, etc., etc., etc. And in this case, we even have, the usual thing. We count 3. No matter which way we go, we see that this methyl group is on the second one. So we go all the normal naming principles with the new rules we find. It's similar naming the alkanes. Halogen is treated as the smallest side chain, should be addressed if its position should be have potential for confusion. So if we go over here, is there potential for confusion in this one? Probably not, because no matter which way we start counting, this always ends up on 2. We start over here, might have a problem there, right? We start on this one, definitely will have a problem if we don't do the smallest number thing. So the simplest of the alkyl halides would include the compound chloromethane or methyl chloride. We have carbon, we have 3 hydrogens, and we throw in Chlorine. Okay, we throw in chlorine. The continued replacement of hydrogens and methyl chloride by chlorination eventually yields methyl trichloride or trichloromethane. We see that we've gone from 1, 2, 3 chlorines, and finally tetrachloromethane or carbon tet if we replace all of the hydrogens with chlorine. Carbon tetrachloride is a hell of a good organic solvent. It's not flammable. It was used in fire extinguishers. And then someone found out that its vapors are toxic and killed people and decided that maybe that's not such a good idea after all. Folks, thank you for your attention. We will see you next time.